So welcome everyone to our last seminar series for last seminar for the series for winter. Today, I'm excited to present my colleague Samarjit Chakraborty, who is the Kennan Distinguished Professor and Chair in the Department of Computer Science at University of Northern Carolina at Chapel Hill. Beautiful place, by the way. Before that, he was Professor of Electrical Engineering at Technical University of Munich in Germany, where he also was a chair of real-time computer systems for more than 10 years. Before that, he was an assistant professor in computer science at the National University of Singapore for 5 years. You've been at beautiful places, by the way. I was in Singapore for the CDC. And his research are probably best described as a random walk, as he writes, through various aspects of designing hardware and software for embedded computers. I should say he's a fellow of the IEEE and also received the 2023 Humboldt Professorship Award from Germany, which is a very prestigious award. With that being said, Professor Chakraborty, welcome.
Yes, thank you. Thank you very much. Yeah, I have never been to UC Santa Cruz, so hopefully I will be there in person at some point in time. But I'm very glad to get this opportunity to give this talk. So this is not a talk I have given many times in the past. In fact, I have just given it once so far, which was last month at Boston University. And this is actually based on I have designed this talk based on a proposal that I'm currently writing. So, I also have this motive of getting some feedback from all of you to be able to incorporate in the proposal. Okay, so let me start and then I'll talk about what exactly I'm trying to write in the proposal. And part of it is based on work that, preliminary work that we have done, which goes into this proposal. Okay, so given that I come from Germany and from Munich, I have had quite a bit of collaborations with the automotive industry, the German automotive companies, and now I have multiple projects with General Motors. So a lot of what I'm going to talk about is the more recent work is done in collaboration with GM. So currently, if you look at any modern car, these cars have, between 100 to 200 electronic control units, which are boxes with, multi-core processors these days. These boxes are all connected by, a complex network made up of different kinds of communication buses. These might be CAN, FlexRay, and more recently, there is a lot of automotive Ethernet that is being used. And this architecture, this highly distributed architecture, is currently used to run over hundreds of millions of lines of software code. And the algorithmic core of the code and the functions it implements, they essentially implement several distributed control applications. Now, these control applications might come from the safety critical domain, from the driver assistance domain, or from the comfort domain. But the point to note here is that this huge volume of code essentially implements things that are centered around different kinds of feedback controllers. Now, I am sure I don't have to show this slide here because, all of you are, better equipped with control theory than I am. But, just for the sake of completeness, essentially, we have a plant or a system, and we would like to impose some sort of a desired behavior on the system. And we do that by designing a controller. So we periodically sense the state of the system using that sensed values. We compute a control input, and we use that control input to actuate that system. And by appropriately designing the controller, hopefully we are able to impose a certain behavior on the system. Now, I would like to, show you an example at this point. And this is a setup that we had built earlier. Can you see the screen? So I'll switch on this video. Now, essentially what you see here is a magnetic levitating ball. And our goal, the behavior that we would like to impose on this is that we would like this ball to levitate in the air. And in order to be able to do this, we need to appropriately adjust this magnetic field. Now, the interesting part of this setup is that we sense the position of this levitating sphere using a camera. So we sense the position using a camera. This camera is a gigabit Ethernet camera, so it captures, very large number of frames with high resolution, and these frames cannot be processed in software. This is way too much data, and the timing constraints that we have are so stringent that you cannot process this in software, but this processing is happening on an FPGA board in hardware. And then based on the location of the ball or the position of the ball, the magnetic field is adjusted in real time. So let's, have a look at this. And this is a surrogate for lots of different applications, which are very time-critical control applications that occur or arise in the automotive domain. So this is where the ball is placed, and you'll see that there are all sorts of disturbances because of which it shakes a little bit. And now you see it is levitating in the air. And using this camera, we track the outline, and on the basis of the position, the magnetic field is appropriately adjusted. And if the control input is not appropriate, then either the ball is going to get sucked into the magnet or it's going to drop, and all of that needs to be taken into account. So this is the kind of system that we are interested in designing. Now, in designing the system, as I explained, on one hand, you need to design an appropriate controller. But on the other hand, there is the software implementation of the controller. There is all the image processing that needs to be done. And all of these algorithms need to be implemented on some sort of a distributed embedded platform. And while there are lots of tools like MATLAB, Simulink, Modelica, etc., that are used for designing the control algorithms, simulating their behavior, and then ultimately generating code, then there are also lots of design tools that are available for designing the hardware platform on which all of this is implemented. And on the right-hand side, we have listed some of these tools. These are, for example, tools from Mentor Graphics or Electrobit or DSpace or Cadence. And I will show you like a screenshot. So here, this is a screenshot from MATLAB Simulink. And once you simulate the behavior of the controller, you are going to see how the system evolves in the state space. And this yellow line kind of gives you an idea of how this system behaves. Similarly, we could also have a screenshot of the design tools on the right-hand side, the tools that are used for designing the embedded platform. And here, this is a screenshot from a tool called SimTools or SimTarget. And the point I would like to highlight here is that there are really hundreds of parameters whose values need to be determined in the process of designing this hardware platform, right? And these parameters could relate to, how are the different components of the system connected? How are the software tasks on each component being scheduled? How are the different communication buses like, CAN or FlexRay or Ethernet? In the case of an automotive domain, how are these buses configured? What kind of scheduling policy should be used in these buses? What are the parameters of the scheduling policy? So there are literally hundreds of different parameters that need to be determined. And based on the choice of those parameters or the design of the platform, the controller is going to experience some sort of timing behavior, right? And usually it is not just timing. There could also be other kinds of factors that get influenced. This could be numerical accuracy. In the case of machine learning algorithms, again, part of that might be timing, a part of that might be the accuracy of the estimation. So the behavior that the control software experiences heavily depends on the choice of these parameters or the design of the embedded platform on which these controllers are implemented. Now, it turns out that if you just simulate the behavior of the controller without taking into account all these intricacies of the implementation platform, the behavior that you might get is indicated by this yellow line. Whereas the moment you take into account all of these intricacies of the implementation platform, what you get is this blue light, a blue line, and you see that there is a discrepancy between the two. And the question is, from where does this discrepancy arise? Now, if you look at the design of the control system, on the top, what you have is the design of the controller, which is you have things like system identification, controller design, and analysis. But then what runs on the embedded platform is not the mathematical laws of control, but rather a software implementation of the control strategy. And therefore, for the implementation part, which is marked as software, you generate code. Then there are steps like you partition the code into different tasks, you map the tasks onto different processors, then there you schedule them, and then you do timing performance analysis and check whether the control objectives are satisfied. And if not, then you go back and either redesign the implementation or redesign the control strategy. Now, the way control theory has progressed, on one hand, when the controllers are designed, typically a large number of simplifying assumptions, especially those related to the platform, are made. And typical simplifications could be that there is no delay from sensor to controller or controller to actuator. All the state components are available at the same time. The computing the control law takes negligible or zero time, etc. But as we are moving towards more complex implementation platforms, like the ones that are today available in the automotive domain or industrial manufacturing domain or robotics, many of these assumptions are not true. And therefore, when you simulate the behavior of the controller at the model level, the kind of behavior that you get versus when you implement it on a real system, the behavior can be significantly different. Now, the research question here, of course, is it does not make sense to have all sorts of nice mathematical guarantees at the model level, but not have that behavior or those guarantees at the implementation level. Ideally, we would like to translate all of those guarantees to the implementation level and have exactly the same behavior in an implementation. And therefore, the obvious research questions would be, given this gap between the model and the implementation, how exactly do we quantify this gap? And, in general, how do we, design systems that are safe, even if there is a gap, right? How do you give some sort of a safety guarantee? Now, if you look at today complex autonomous systems, then such systems are made up of a large number of components, right? On one hand, there is control. The control is increasingly becoming more complex. Then there is a lot of machine learning. Your cameras or radars or lidars, whatever the capture, that is passed through a machine learning or a neural network component, which will probably do some classification or some estimation, which then is fed into a controller that computes a control input. There is the design and the processing of the sensors. There is a lot of software. When you translate your models into software, the semantics of the software might be very different from or somewhat different from the semantics at the model level. There are issues related to timing. So all of these components are essentially put together, and that is what results in your overall system. Now, the current design approach is that each component is designed in isolation, and the goal is that each component is designed to perfection. What is the meaning of that? It means that, for example, your timing component that is responsible for doing things like scheduling, the goal is that all deadlines are always met. If you're looking at the machine learning component, the goal is that the machine learning component works perfectly or works as perfectly as possible. It does perfect classification. The goal of the security component is that everything is 100% secure. Now, of course, this makes the design much more simple because there is this separation of concern. You are just concerned with designing the perfect machine learning component, or you are concerned with designing the perfect timing component. But then Once you put them together, if everything is perfect, everything will work, as desired, and your safety properties will be met. But the reality is that designing these perfect components is becoming increasingly difficult to the extent that it is virtually impossible. For a system that is as complex as a automotive electrical or electronic architecture today, it is impossible to ensure that all deadlines are always going to be met. Given machine learning components, the way they are becoming complex, it is impossible to design machine learning components that will always do perfect estimation. More importantly, it is impossible to give guarantees that whatever the machine learning components are going to do is going to meet certain specifications. The same is true for things like security. If you want to guarantee perfect security, then it could be that the cost is prohibitively high to implement in systems that are as cost sensitive as the automotive domain. So the position that we are trying to take is that there is really no need for each of these components to be perfect. So for example, if the machine learning components are not doing perfect classification, we can compensate for that inaccuracy by designing the controller appropriately. If the timing components are not meeting all deadlines, we can probably compensate for that by designing the controller appropriately. If the translation from the controller to the code is not perfect in the sense that the semantics do not match exactly, we can probably compensate for that by having some relaxation in timing or, over provisioning some resources. So the main goal is that if we can coordinate these components better, then this assumption that each of these individual components have to work perfectly, that assumption is no longer needed. And this can make designs way more reasonable and more practical. So in other words, the current approach is that people try to design each of these components perfectly, even if they know that this perfection is not achievable. The design method has nothing in it that incorporates for this loss of perfection. We just kind of hope for the best and have enough design margin so that even if there is a little imperfection here and there, the system will, nevertheless somehow work. But there is no systematic analysis of what happens if each of the systems turn out to be a little imperfect, what kind of design, safety margins are needed. That analysis is missing. So instead of doing that, we would like to take a different approach or a new approach and really bake the imperfection in the design. We would like to make the imperfection a first-class citizen. So therefore, when we are designing the ML component, we are designing an imperfect ML component. When we are designing the timing component, we would like to design an imperfect timing component. So we would really like to have a specification, a formal specification of the imperfections, and then bring everything together and coordinate these imperfections in a way such that we can give formal safety guarantees. And at the same time, because of these imperfections being baked into the system, we claim that we can also design systems that are more cost-effective and more reasonable to design. So with that, I will kind of give you one example of what we have done, and then I will, give you some, high-level ideas of how this can be extended to more realistic or more complex setups. So the current approach in designing this kind of safety critical systems is that, the basic idea is that safety is equated to meet all deadlines. So when you design a safety critical controller, the control theorist designs the controller, determines some sort of, sensing to actuation delay, sampling period, etc. And these values are communicated to the software engineer or the embedded systems designer. And the goal of the engineer when implementing the controller